Hello students. In this video I'm going to take you through some initial conditions for this nonlinear system of ODEs. And so this is really a continuation of another video where I actually linearized this system of ODEs. So what I did in that previous video, and you should watch that so you can understand what I'm doing in this video, is I computed the null-clines for this system, and then I linearized about this equilibrium solution. And when I linearized, I computed the Jacobian to linearize, and then when I linearized, I got this system of linear ODEs, and then I solved that system of linear ODEs. First I looked at the vector field, and I saw that I got this saddle point behavior. I solved the system, and sure enough, I got a positive eigenvalue and a negative eigenvalue, and that is classic saddle point behavior. Now what I'm going to do in this video is I'm going to consider initial conditions in each of these four regions separated by the null-clines. So this region up here is going to correspond to quadrant 1. This region here will correspond to quadrant 2. This region down here will correspond to quadrant 3, and this region down here will correspond to quadrant 4. So I'm going to first pick an equilibrium solution in this region here, which will correspond to quadrant 2. Now watch what happens. If I pick the initial condition 1/2, 3/2, which is clearly in this region, 1/2, 3/2 will be up here. That's going to put us in quadrant 2 in the UV coordinate system. If we do the shift by the equilibrium solution, which was, remember, this EQ was 16/19, 15/19. Sure enough, here we are in quadrant 2. Now what I expect to happen by looking at this flow is I expect it to kind of flow out this way, and I'm expecting V's behavior to dominate. Now V was the transformation variable for Y, so I expect the blue curve to dominate. Let's now plot that solution. So what I do here is I take that initial condition, I plug it in for U0, V0, I get this linear system of equations, I solve it. Now remember, these vectors here were my eigenvectors, so I take the inverse of the P eigenvector and I apply it to the right hand side, which is the initial condition, and I get the values for C, and these are my constants C, and then I plot the corresponding solutions for U and for V. And so here's V, which was the blue curve. Now remember, Y and V correspond to blue, and U and X correspond to red, and sure enough, the V behavior dominates. Likewise, if I look at an initial condition, so I'm going to look now at 3/2, 1/2, and so that's going to put me down here. So that's going to clearly be in quadrant 4, and I'm going to expect flow down, and that flow down in this direction, so that's going to be dominated by U. And so if I shift by the equilibrium, 16/19, 15/19, sure enough, I get something here in quadrant 4, and then I scroll down and I plot this solution, and sure enough, U dominates. That's the X variable, and V is dominated by U. So, and that was V was the transformation variable for Y. So X and U dominate Y and V. The last two I'll go through rather quickly. These are the equilibria. So we're going to see this. We're going to see these two behaviors here. So here we expect them to both be about the same. We expect some kind of equilibrium behavior. And if we take a look, remember 1/2, 1/2. If I shift that 1/2, 1/2 by the equilibrium solution, So that means I'm taking something that's in this region here, and I'm going to shift it down. Then that's going to put me in the third quadrant. I'm going to expect some kind of equilibrium behavior because I want to flow towards the origin. And sure enough, if I shift it by the equilibrium solution, I get that point there. That is certainly in the third quadrant. And then when I apply it, yeah, I get some kind of parity, some kind of equality between the variables x and y. In this case, this is u and v. So I get a little dominance by v over u, but not much. Okay, and then likewise, if I pick a point in the first quadrant, 2, 2, then when I shift it by the equilibrium, it puts me, still maintains a point in the first quadrant, and then I get my constants by solving that system of equations, and then when I plot it, sure enough, I get some kind of parity again. In fact, they actually cross, so they flip-flop their dominance, and that was something that was up in this region here. 2, 2 is over here, so we expect some kind of flow towards equality, and sure enough, there's flowing towards the equilibrium solution there. So that's how you analyze this behavior of these solutions for each of the separate initial conditions. So just a quick wrap up. I want to go back up to the top of the model here, and I just want to show you what's going on here. These are called competition models. If you ignore the 1/4 x and the y here, you notice that you get x primed equals x. The solution of that is exponential growth. You can solve that by separation of variables. You're going to get e to the t here. And so if this x was by itself, it would just grow unchallenged. Similarly for y would grow unchallenged. However, if x gets multiplied by x, we call that an interaction term. So x is interacting with x. As soon as x starts to interact with something, it starts to decay. You get a negative behavior. That's a negative interaction. And likewise, if x interacts with y, it's certainly going to be competing with y, and so you're certainly going to get some kind of negative interaction there, and you expect some kind of loss in growth. Likewise, when y interacts with x, it competes, so that competition is indicated by a negative sign here, and you're going to get some kind of negative behavior detracting from your growth. And likewise, if y interacts with another y, then you're going to expect some kind of competition amongst the y's with one another even. The 1/5 and the 1/4 indicate that when x interacts with x, it's a smaller, it's a diminished competition, but a competition nonetheless. More vigorous competition, higher magnitude with y, and likewise when y interacts with x, it's a higher magnitude than when it interacts with itself, with its own kind. So these are called competition models. And so that's why I use terms like what you saw here. You might have some kind of parity in these two quadrants, but in these quadrants, in this one certainly V dominates, and in this quadrant U dominates. And that's why I used that kind of language when I showed you these single plots of the component by component. The bottom two were where they wanted to flow towards equilibria, and you got some kind of parity. And then in these top two systems, you saw that either U dominated or V dominated. All right, so that's the analysis of the system with initial conditions. Okay, good luck.